Let's begin. Today I'll be going over topics that can show up on the test for the calculus-based question. There's one calculus-based question. It's the last one. Shocking, isn't it? And it's going to be using either Coulombs law or Gauss's law. Now, somebody could very validly say, but we also had transient circuits in this time. Yes, we did, but we'll also have transient circuits in the time of the next test as well, and so that's where it will be a possible thing is on the next test. So I want to go over the two laws, trying to help you decide when to use each law and how to use each law. So I only have like 4, 5, 6 slides going over the laws and how to choose and how to apply, and then I will have you suggest. I didn't want to bring out my own problem because then you have biased things like, well, I've already written the test question. Do I show them the test question and make a mockery of the test? Or do I show them everything but the test question and then let them, And so I'm just going to have you guys suggest problems to solve. And that way there's no quandary. I just do what you guys want to know. So first is, how do you determine between the two? The two laws are equivalent laws. They're essentially the same law, just written in different forms. So anything that you can solve with one, you should be able to solve with the other. The difference is which is an easier application. And so when you're sitting down to solve a problem, the first thing to do is to say, which one is this problem going to be easier to solve with? And that comes down to symmetry. If you have a problem with an exploitable symmetry, that is a problem that has spherically symmetric charge distribution or cylindrically symmetric charge distribution or planar symmetric charge distribution, and you had all of those on that homework assignment, right? If you have something that has one of those symmetries, then it's likely to be much easier to solve it with Gauss's law. Not necessarily going to be hard to do it with Coulomb's law, but much easier with Gauss's law. If you don't have one of those symmetries, it's likely to be much easier to solve with Gauss's law than with Coulomb, or I said that backward, didn't I? If you do not have one, it's likely to be much easier to do it with Coulomb's law than Gauss's law. And there are some problems that just aren't easy either way. Of course, for a test, I'm not going to give you something that's just not easy either way, because you could spend the whole test period doing the one problem. So your test problem is going to be something that's reasonably simple to do. And please keep in mind, reasonably simple doesn't mean it should be easy for you, and if you don't get it in 5 minutes, that you're not up to date. When I say reasonably simple, I mean it's something that you can do, not that it's, what's 3 plus 5? Okay, so that's how you decide which one based on the symmetry. So let's look at what each law is. Now, Coulomb's law, the way we first introduced it was in the algebra class, and we had, I'm still on color that Jordan requested. That's the way we first learned Coulomb's law. We learned it as a force equation. It's really, in everything except for your most trivial of instances, more useful to use Coulomb's law as an electric field equation. That is the electric field due to a point. This is the force between 2 point charges. It's more useful to use it as an electric field equation that says the electric field due to a single point charge is kq over r squared, where q is the charge of the one charge, and r is the distance between that one charge and the location you find the electric field. Now, both force and electric field are vectors, and these equations aren't showing the directions. What do we use for direction?
Plus or minus.
If it's one-dimensional, yes, that's a correct answer. I always say I use my brain. We know, everybody here knows, opposites attract and likes repel. So the direction is only going to be attractive or repulsive. And so I look at my charge. If it's a positive charge, so I'm doing the electric field, it's always pointing away from the positive charge. So I just have to determine what direction is away from the positive charge. That's the direction it points. If it's negative, it points into it. So you do that. So I like I say, I just use my brain at geometry. There's ways, I'm sure, of describing it with the right mathematical terms, but just the fact that I understand directions, I use that for the directions rather than trying to complicate things by having the directions in my equations. So that's just the magnitude equation, and down at the bottom you see for calculus, if you have a distribution of charge, you can't do a single point charge if it's distributed. And so that's why we have to have the differential form here, dE equals k dq over r squared, and then we integrate over all of the volume that has charge, that is, we integrate over dq, and we find what the electric field is. But before you do that, you do have to pay attention to the directions. So my actual application here, oh, come on, focus, baby. There we go. It's not filling quite the page, but I'm afraid to change it again. So basic rules. First, after drawing a figure of your charge distribution, determine if your charge is distributed over a line, over an area, or over a volume. So in your homework, that was one of the questions you had to answer, right? Charge distributed over line, area, or volume. In all cases, you're still going to have the integral of dq, but if it's distributed over line, that integral is just, lambda ds. I make sure I have the right symbols. Lambda ds, where lambda is the charge per unit length. So if you have a wire, hot tip, wires are lines, and the wire has length L and charge Q, then what is lambda going to be? Charge over length, so it's just Q over L. If you have a cube of volume V and charge Q, which of those three situations are you dealing with? It's which one? Rho dV. It's the 3D version, the volume version. And so you have rho dV, and then rho would be Q over V. And of course, you have the one in the middle. If it's spread out over the surface of an object, then you have the mu dA, where mu is the charge over the surface area. So you want to make sure that you identify which type of charge distribution you have. Then I said here, use geometry to break into components. Solve each component independently. So for instance, in problem 1B of that homework set, you had your point was not above the line but off to the side. And so you had both vertical and horizontal components to the electric field. And so you then calculate, okay, so the horizontal component is the total electric field times, cosine of your angle. The vertical component was the total electric field times the sine of the angle. And then you did the integrals for dEx and dEy separately. And miraculously, you found that they had the same Ex was equal to Ey. Wasn't that miraculous? You weren't shocked? Nobody was shocked. Oh, well. So you found the direction was at a 45-degree angle based on doing those two separate integrations for the horizontal and vertical components. So, that's the mechanism. Yes, Gabriel.
Is it fair, unless this is where you're going, but like one of the previous test questions that you had on Moodle, it had a semicircle wire. Mm-hmm. Is it fair to make an argument that the X components are going to cancel themselves out based on the symmetry in the X direction, or do you still have to solve?
No, it's fair to make the argument, provided you did it correctly. You didn't apply it incorrectly and
But you can say based on the symmetry of this, the forces will be equal and opposite.
Yes.
And you won't have that.
And you want to be intelligent. We made those same type of arguments every time with Gauss's law. And so, yes. So, for instance, if I were to give you a complete circle and say, what's the electric field at the center? The prudent person says, based on the symmetry, for each point over here, there's a point over here that's giving you an equal and opposite electric field so that the total is 0. And you're done. Right? You answered it with perfect logic. You don't need to do math to show that. Was there a question? Okay. Now to Gauss's law. Gauss's law is relating the electric flux to the charge enclosed. It's based on the idea that if you have more charge, you have more electric field, and there's a relationship between the electric field produced and the charge, which, once you define an electric field, makes perfect sense. So always identify the symmetry you have when you start with the Gauss's law problem, and you can use it outside of those 3 symmetry situations I talked about, but it's not going to be as easy. So it's usually going to be easier to go to Coulombs law if you don't have one of those. So when you apply Gauss's law, start by identifying your Gaussian surface. And that Gaussian surface can be a confusion. You've now gone through and drawn pictures and whatnot for Gaussian surfaces many times. The Gaussian surface is not a physical surface. You're not saying, I have the surface of a sphere. That's my Gaussian surface. The Gaussian surface is a surface that you imagine to be there for calculational purposes. So you say, okay, I'm going to make an imaginary surface that has the same symmetry as the problem has. And then on that surface, I'm going to do calculations of the flux going through it and the charge enclosed. So 2 separate calculations that you must make. Calculate the charge enclosed by that surface, all of it, and calculate the electric flux through the Gaussian surface. And then you apply Gauss's law, which sets the 2 equal to each other. So I wrote Gauss's law 2 times here. This is the electric flux. That's an L. And this is how you calculate the electric flux. And of course, on the other side, the charge enclosed. I just wrote a volumetric distribution because given your symmetry, well, you are likely to have a volumetric distribution of one type or another. So once again, you had experiences with using this law with cylindrical symmetry, with spherical symmetry, and finally with planar symmetry. I think that was the order that you had the problems. And for the problems that you did, where did you actually use calculus in your solution? Okay. The actual calculus you did was in this. How did you do these without calculus? How did you calculate the flux without calculus? By making symmetry arguments, we were able to evaluate the calculus without doing any calculus. Right? We wanted surfaces where either the electric, and I have those up there, the electric field points in the plane of your Gaussian surface, which means the 90-degree angle between the area and the electric field. Well, because of that dot product, if there's a 90-degree angle between them, then it's 0 for the flux. Or if you have a constant angle that's not perpendicular and a constant electric field. If you don't have a constant electric field on your Gaussian surface, you better have that perpendicular or you're lost. Right? If your electric field is changing over your surface and you don't know how it's changing, you can't do the flux calculation. So that's where choosing the right surface becomes important. And as I said, it really comes down to trivial choices once you have experience. You have experience of one choice of each option. So you don't have huge experience in applying this. But you've seen, okay, this situation, it's spherically symmetric, so I'm using spherical surface. So because of the symmetry, it can't matter what my theta or phi are, it can only matter what r is. And Thus, on a spherical shell concentric, the R is the same. It has to have the same electric field. Things like that, you have to make those arguments. So if it's on the test, make sure you give justification for your symmetry arguments. Don't just say, by symmetry, flux equals this. Make sure you say, by symmetry, this has to point this. Make sure you give the reasons why symmetry tells you that. All right, now it's your turn. What would you like to explore? I don't know why it's defaulting to dark gray. I also don't know why the first time through it won't work. I figured it out that you just have to do it more than once and then it'll work. So, name something that you want to see explored, a question you have. I will do as requested. Because oh, good. I'm done with my prepared portion. Now it's just your questions. Yes, Aaron.
Can we do a planar symmetry one using maybe like a box and then maybe a cylinder, like show a couple of different Gaussian surfaces and how you would use it? Well,
planar symmetry, it has to be infinite planar. You break the symmetry. So a box wouldn't have that symmetry.
But you said if you have like a slab,
yeah,
then you can use a box as a Gaussian surface.
Oh, so okay, I misunderstood the question. I thought you were saying I have charge distributed on a box or charge distributed on a...
Oh, yeah, no.
Yeah.
Like
okay, so sure. So start by... There's my plane. It goes on forever, and I drew a little white line in the center. Intentionally, perfectly intentionally. Okay, so first... What's the difference in using a box versus a cylinder? If I use a box, my box has a total of 6 surfaces. And so when I put this in here, based on the symmetry, my X and Y, assuming Z is vertical, my X and Y can't make any difference because if my plane is infinite, my charge is spread out infinitely, then it doesn't matter where my X and Y are. It's the same position as far as symmetry goes. So only Z can matter. And because electric field has to point away from positive charge, just going with the same situation we had in our homework, it was positive charge, then I know that my electric field direction has to be going like this. Hey, look at that. We're full of problems today. You may not have noticed, but it stopped reading the pin. And so close the app, open the app, and it will read the pin again. So the electric field is going like that, and underneath, of course, is going like that. So I need to place the box. So I'm going to have the electric field is either parallel to the plane of the side or normal, parallel to the area. And so it's pretty clear that that box is going to have one surface that essentially is parallel to the plane and opposite. Rotating it shouldn't matter. And then I say, okay, for the top surface, I'm going to have the electric field is parallel to dA. And because the top is the same distance away from the plane at all points, the electric field has to be constant. So integral of E dot dA becomes E times integral of dA becomes EA for the top. Now for the sides, because the sides all have the direction of the area is perpendicular to the direction of the electric field, then the flux on all the sides is 0. I've now covered the difference between the cylinder and the cube or a box because I had all of the sides that were, the four sides that are going around the edges. On the cylinder, that's just one side. And so for the cylinder, I just have to say the side, whereas for the cube, I have to say the four sides that are top and bottom. That's the difference. Now, the last thing about this is where you're going to place the bottom of your cylinder or your cube. Well, once again, it doesn't have to be a cube. It can be a square, rectangular, parallelepiped, right? Those are the right words. Where do I place the base? And there are two correct answers. So let's just do a random polling. When you did this, how many people put your base symmetric up below from the top? So you have the base is below, the top is above, and it's symmetric between the two. None? That's one of the two valid ways of doing it. The other valid way then must be what everyone else did. Where did you put your base? Where?
I put my top at the 0 line and then the bottom all underneath that.
Okay, top at the 0 line.
Yeah, can you
I
try it?
say the base. Yeah. Yes, I indeed will. So to actually place this, I think what you said, Aaron, was that you put it like this.
Mm-hmm.
And now I'm only showing a two-dimensional picture because A, I have no artistic skills and that's easier for me to draw. And B, we've established that the sides don't matter. It's only the tops and bottoms that matter. So as long as I have those shown, that's what matters. And then you would have this distance here, of course, is Z. The way I was describing it was like this. And the final way of describing it, or of doing this, would be to have it where Z is just going to be the magnitude. So I'll put Z up here. And then it's symmetric. So once you have that placed, then your work becomes, and of course I didn't make my slab big enough to have it so I could draw it with the cap inside of the slab. Your picture, assumingly you drew the slab big enough that you could draw a little box that was not as tall as the half thickness of the slab. But then I go through, and for this one here, the flux for the top, using top being the highest part, equals 0 because based on symmetry, E equals 0 at center of slab. And then the flux on the side or sides, depending on if you chose something that has square top. You could have used a hexagonal top if that's what you really wanted, right? Because based on symmetry, okay, so I have my reasons for each one of those, not just because of symmetry. So that's what you have for the first box. The second box, all you got to do is flip the words top and bottom, and it's going to be the same answer. The third one is the one that's going to be unique because you're going to have flux top equals flux bottom. equals E top area top. And once again, because symmetry says the same as below, and it's only distance. It doesn't matter if you're going up or going down. The strength can only depend on the distance away. Its direction is opposite, but the areas are opposite. So you have a little more to add on that one. So this one here, your flux is going to be 2 times electric field top, area top. These two shapes here, your flux is 1 times that. Of course, when you do the charge enclosed here is twice the charge enclosed there. And so those twos cancel out and you get the same answer. You had a question, Gila? No, okay, I thought I saw you. So finishing up then, I will go back to the blue way because that's how everyone did it. Charge enclosed is equal to integral of rho dV, which is equal to the area times integral of rho dz. Rho was a constant, I believe, in that problem, wasn't it? And so that just became a rho, and then my z goes from 0 to d if I'm outside. If I'm outside, the charge ends at d, the half width in that problem. D. And so then putting everything together, I have my total flux equals E bottom, area of the bottom is equal to area. And what is this area? It's the same area of the bottom times density times D over epsilon 0. And I get my answer.
So you can leave it in variable form like that. You don't even have to, well, I guess.
I didn't give you the value of rho or D.
But like the pi r squared substituted.
Oh, right. Yes. Because the area has to cancel. If it doesn't cancel, you did it wrong, right? The size you chose of your Gaussian surface cannot change what the electric field is at a given place. And so if the area didn't cancel, you know you made a mistake. So yeah, you don't have to break down further. Okay, that was one problem. Someone else? Okay, for a sphere. So again, Gaussian. So for a sphere, my spheres look surprisingly like circles because I've got those kind of skills and I have a tool that makes a circle. Okay, not oval, circle. So I have a sphere. Now let's make life at least a little more interesting. Let's make our problem something like the one that you had with the cylinder. So I'm going to do like you had with the cylinder, except for with, oh goodness. Bad plan, bad plan. When you're as good as I am with the pen, I'm just going to make a second one like, oh goodness. Okay, that's what we're working with. And we're going to put at the very center charge plus Q. And then I'm going to have this filled with rho, where rho is equal to rho 0 R. So as the radius gets bigger, you have a higher amount of charge. And it's just linear with radius. So that rho is only between these two here. And now if I want to apply Gauss's law, you notice that with the cylinder one, it talked about regions. How many regions am I going to have where I have a distinctly different result? And so when you look at this, how many regions do we have that will have a distinctly different result?
Inside the first one, inside the second one, outside all of it.
Yeah, we have 3 regions that are going to have distinctly different results, not just 2. Those regions will be region 1, region 2, and region 3. The first one is inside where it has a charge in the center and then nothing. The second region is in the region where we have charge distributed. And then the third region is outside of that where it's going to look like a point charge. And then for each of those regions, I need to define my Gaussian surface. What's the shape of the Gaussian surface going to be? Yeah, I'm going to write on here the word sphere because if you just look at the pictures, you won't know that it's a sphere by my pictures, will you? So I use a spherical Gaussian surface. For each region. So let's do the flux. The flux is based on my symmetry. My symmetry is the same regardless of which region I'm in, right? And so my flux calculation I can just do once. The symmetry says that it's equal to EA equals, well, let's do the whole long thing. It's the integral of E dot dA, not D, yeah, E dot dA. But because due to symmetry at constant radius, E is constant and direction is radial, parallel to dA. So I did 2 symmetry arguments there. One, at constant radius, you have to have constant electric field if you have spherical symmetry. And number 2 is with the spherical symmetry, the direction of the electric field has to be radial, just going in or out. And so then the final step, that's equal to E times the area, which is 4 pi r squared. And notice I have to put in the 4 pi r squared here because I'm not going to have that same area on the other side of my calculation. So then I have to go to, for each region, region 1, charge enclosed equals. So region 1, I'm enclosing that one single charge. So what's the charge enclosed? Yeah, plus Q. No calculus there. Region 2, Q enclosed equals, it has the plus Q, right? That's still enclosed. But then I have to have plus the integral of rho dV. Now let's make lives as easy as possible. Most people here, in fact, I think everyone here hasn't taken something where you've focused on triple integrals yet, right? Or maybe it's come up by now, but hadn't come up. Okay.
We're coming through right now. It's like
Well, if you're not comfortable with triple integrals, we can just go to the, because of symmetry, this integral is integral over radius from, oh, I didn't label. Let's say this is A and that is B. So it's going to be, the inner radius is A out to wherever I am. So I'm going to put R region 2. And then the area for the sphere is 4 pi r squared. dr. Right, so I'm doing the integral, the integral of the charge times the area times dr. So area times dr, the surface area times dr is dV. If it's spherically symmetric, that's a perfectly valid thing to do. People that I worked with, I show you have this full integral with dV is r squared sine theta dr d theta d phi. And when you do the integral of sine theta from 0 to pi, that gives you 2. And when you do the integral of d phi from 0 to 4 pi, or 0 to 2 pi, that gives you 2 pi. 2 times 2 pi is 4 pi. That's the 4 pi I just wrote. And then the r squared was the r squared that was part of dV. So it comes out identical. This is just a way of making it short. And so now I can actually do my calculation. My rho was equal to rho aught r, so it's going to be rho aught integral from a to r2 of, I can bring out the 4 pi as well. And final step. So there's my charge enclosed in region 2. And just like with the cylinders, region 3 is going to be reasonably trivial. What's the difference between region 2 and region 3? Yeah, you end at B. You don't go out to R3 because the charge distribution ended at B. And so it's going to be exactly like what we did before, except your R, R2 becomes B. And so it's just going to be Q plus pi rho 0. B to the 4th minus A to the 4th. So I found my charge enclosed for each of the 3 regions. And now I just need to combine them. And so region 1, E 4 pi r squared equals Q over epsilon 0. E equals Q over 4 pi epsilon 0 r squared equals KQ over r squared, which is absolutely no shocker. It's the same as it is for any other point charge. Then going to region 2, E 4 pi r squared is equal to Q plus pi rho 0 Notice these R's are the same R. I can put the R2 there, or I can just drop the 2 on both, which is easier nomenclature. And so solving this, the first term gives me the same KQ over R squared. And the second term gives me, my pi's are going to cancel. I'm going to leave the 4 in there. And yeah, you can multiply that r squared through. And you have one that's r squared, one that's 1 over r squared. But that's my electric field in region 2. And I actually usually am smart enough to put a region 2 marker there. And then finally for region 3, and I'm going to cut right to the chase. both of these are 1 over r squareds. And if you go through and do the calculation, you can prove yourself pretty quickly. It's just K total charge enclosed over r squared. So that would be going through and doing it for each of the regions for a spherical problem that's different than the spherical problem you did. It was somewhat more complicated because you had multiple regions. That work for you, Carrie? Okay, we got 10 more minutes, so we have another question. Can we do one with Coulombs law? Name one with Coulombs law. Dual wire. In what geometry? What?
It doesn't matter.
Something that's a little bit more than a semicircle. So semicircle that it's starting to come
Okay.
back.
Okay, so something that goes like.
Yeah.
So we'll have like.
Centered on the origin.
So it's filling all but theta. And there's lots of ways you can relate the length to theta. Easiest is we have theta is equal to 2 pi minus L over R. Because an arc, the angle for an arc is L over R. And so if you have a complete circle, it's 2 pi. And so the amount that's missing is 2 pi minus L over R. Okay, so there's our distribution. We're going to have Q is equal to Q. Q distributed. Okay, there I've spelled everything out, right? So we're ready to get going. So step one is going to be use Coulombs law because no useful symmetry. So now that we've decided that, we know that dE is equal to K dQ over R squared. What's dQ?
Lambda ds.
Okay, it's going to be lambda ds, where lambda is equal to Q over L.
How did you get that?
Because it's a wire, it's a linear distribution of charge. And so for linear distribution, you use the lambda ds, where lambda is defined as the charge per length. And so I gave you, it has Q distributed over length L. So charge per length, Q over L. Okay, so I have my lambda, I have my dq. What about R? What is R equal to? R is the separation between my point where I'm finding it. Oh, I didn't say find E at center. Have to specify that. And it was specified before, but I didn't write it down. So R equals R because the distance from the center to any piece of wire is just R. So I have some little piece of wire out here of length ds. And we're going to have some d theta that's related to that ds. And once again, using the definition that theta is equal to, well, I'm going to use S over R now because of the right variables. Then d theta is equal to ds over R. And so I can substitute that ds is equal to R d theta, because I like to do my integral over the angle. It's going to make my life generally easier.
And you're using S as distance.
S is the distance along. See, I got the ds identified here. So S is the distance along the wire. So now that I have this, putting all of this in, I'm going to have dE magnitude is equal to K lambda RD theta over R squared. I think I did everything right there. We can cancel one of the R's. And so there's my dE. Now I said we need to break it into its x components and its y components. So I need to identify my x and y directions before that makes any sense. So there's my x and y directions, and this is the origin. And this is as good a time as any. Well, I'll do it breaking up, and then I'll use the symmetry argument that Gabrielle already spoke of. So dEx, I'm going to define theta as the angle from here. So why do I do it from there? Well, it makes my life easiest. It's the angle from the x-axis. And so the x component, how do I find the x component? If the magnitude, the hypotenuse is my dE, then what's the x component going to be? Yeah, dE cosine theta. So dEx is equal to dE cosine theta is equal to, nice, K lambda over R times cosine theta d theta. And what about dEy? Sine theta. Now, the symmetry argument, which will save us about 10 seconds. Based on the symmetry here, I chose this to be symmetric, so I have the same amount missing on both sides. Hence, what symmetry argument can I say?
This direction is 0.
Yeah. So EX equals 0 because symmetric about y-axis. All right, symmetric about the y-axis. You're going to have the same thing on the left side as the right, canceling each other out. EY, I'm going to have to actually integrate. What are my limits of integration? I have to work with the definition of theta that I started with, which probably wasn't the best choice when it comes to actually these limits, but it is what it is. So if this here is 0 degrees, horizontal 0 degrees, and I'm going down to this point, then I'm going to have minus pi over 2 plus half of that theta m, the theta missing. So I'm going to go from minus pi over 2 plus 1/2 theta missing up to, and what's my other limit? Well, it would be 3 pi over, it's a lot easier to just go 2 pi minus the same thing. Wait, no, you're right. I was wrong. You're right. 3 pi over 2 is straight down here. I was thinking it was, yeah. So 3 pi over 2 minus 1/2 theta missa. So my choice of where to put my reference point turns out to be poor, but will survive. Oh, hey, look at the time. So now we integrate. What's the integral of sine theta d theta? And so this is equal to, oh, wow. My brain really put that together wrong. I put them in opposite order because of the minus sign. And now is where you start taking your geometric identities that if I have cosine of some angle that's equal to sine of that angle plus pi over 2, and you use that identity to make that pi over 2 3/2 or 3 pi over 2 shifts and make it simple. And we're out of time. I don't want to go through those steps. It's simple. It would be correct to leave it this way.